My name is Manish Gupta, and today I'm going to talk about Composite Sketch+Text queries for retrieving objects with elusive names and complex interactions. This work is in collaboration with folks from IIT Jodhpur, Prajwal, Kshitij, Kriti, and Professor Anand. So let's get started. So what is this problem of complex queries? Let's say I want to find this picture, right? So in some ways, I want to find this animal digging into the ground. So now, due to lack of vocabulary, I really do not know what do I call this animal. Do I call it chipmunk, badger, weasel, mongoose, or skunk? What do I call it, right? And I want to find these kinds of pictures, right? So the first thing that I can do is to search like this on a typical search engine, right? Small mammal with striped, blackened, long snout digging in the ground, right? So, but then I'm disappointed because I see images of this kind. I don't really find this particular animal, but other similar animals, okay? And then I draw a sketch. Maybe I can basically have some sort of retrieval systems which can take sketches as images as input and then find other relevant images that match this sketch. However, I still cannot find this animal. Maybe I can find this animal, but it's not digging into the ground. I wanted it to dig in the ground as well, right? And that is where basically we come up with this system called as CSTBIR, which is basically Composite Sketch+Text based image retrieval, where we can actually give the sketch as well as the text so as to retrieve relevant images. These queries, this kind of a system is really relevant for complex queries which contain these two things: difficult to name but easy to draw objects like Numbat, the guy Numbat here, right? Or difficult to sketch but easy to verbalize objects, attributes, or interaction in the scene, like digging in the ground. Right, very difficult to sketch digging in the ground, right? But easy to express it in text. So for queries, complex queries like Numbat digging in the ground, this kind of a system is really applicable. Now, there is some related work. For example, there's work on sketch-based image retrieval, where you can just provide the sketch and then retrieve images. And traditional methods have been CNN-based, but recent methods have been transformer-based methods and deep Siamese models with triplet loss. There are some specialized forms of SBIR as well, like zero-shot SBIR, fine-grained SBIR, category level SBIR, and so on. Similarly, there's related work in text-based image retrieval field. A lot of related work there, right? So where the idea is you give a text as the query and you want to retrieve images by aligning query text and images using visual BERT, will BERT, these multimodal models or cross-attention based models. You can also provide object tags in those images and therefore do a good match. Or there has also been work on contrastive learning methods and zero-shot learning methods. Okay. Lastly, what is most relevant to our work is multimodal query-based image retrieval. So here the query is multimodal, like in our case. However, the multimodal definition is different in these pieces of work. So for example, there is some work on reference images and category text supplied as input for image retrieval. So remember, we don't pass really images, we pass sketches. Right? There's also work on passing speech and mouse traces as the query. Now, of course, we have to do nothing with speech, right? And then there is also work on detailed sketch and text input. So this is also Sketch+Text input like our work, but then the sketches here are pretty detailed and also the text is complete, right? Unlike our case where the sketches are pretty crude in nature and and the text is not complete. It's partial. Okay. So there's this work in e-commerce product images where sketches have been very, very detailed, extremely detailed, or work on particular product-focused images, right? So as compared to other pieces of work, in our case, we basically take Sketch+Text as input and not just sketch or not just text. And we basically have sketch focused on a particular object, while other pieces of work have like sketches of the entire scene, which are super detailed, right? And the text in our case is incomplete and complementary compared to complete text in other pieces of work. And in our case, also we want to find images in or find those objects in scene images rather than targeted focused object images only. So that's how our work relates with other line of work. Now, to be able to do this work, we wanted to create a data set. So remember, our problem is as follows: given a hand-drawn sketch and a complementary text T associated with it, and a database of n number of scene images, we want to find the most relevant images, top K images, based on relevance of the composite Sketch+Text query to that image. Okay. So the way we generate this data is by doing intersection between two interesting data sets, popular data sets. So one of them is visual genome. So we get our natural images and text descriptions from there. We get sketches from another data set called as quick draw, right? So we take the intersection and then that gives us, our data set, which we call as the CSTBIR data set. We divide the data set into three parts: train, validation, and test. But before that, a little bit of a look at the statistics of the data set. Our data set basically covers about 258 different object types. There are 108K unique images and 562K sketches. So the data set is pretty large in that sense, right? Unlike several other data sets where the area covered by the query could be 100%, in our case, it's basically scene images. So we, the current object that the user is searching for just covers about 37% of the area. Okay. These are some of the examples from our data set. So, a pair of something climbing cliffs on a sunny day. Well, this something is Markhor. Now, did you really know that this guy is called Markhor, right? And then this thing is basically called as penny farthing. And this thing is basically called as Bodhran, right? Now, so difficult to name objects, right? So we divide the data set into 3 parts: train, validation, and test. The statistics are here, and more details in the paper. But importantly, test set, we have like 3 different test sets. Test 1K with 1K images, test 5K with 5K images, so slightly larger gallery. And then we also have an open category test set, which basically contains the 70 objects which were not seen at the train time at all, right? They are many of them are difficult to name objects, extremely difficult to name objects. Okay. So here's some of the sketches. So, there are some of the sketches that you see, for the open category test set, we also created sketches ourselves manually. So there are some of those that you see here. Very crude sketches and, drawn very quickly, maybe in 30 seconds. Okay. So our second contribution is the model, the STNET model for doing this composite sketch plus text based image retrieval. Okay. So model basically contains 3 important transformers, 3 important encoders in that senses. One is a text encoder, sketch encoder, and image encoder, of course, right? So the first part is basically combined as an encoder in that senses. So sketch plus text query encoder in that senses. So it comprised of a pre-trained clip text encoder and a pre-trained VIT vision transformer based sketch encoder. However, this vision transformer, although we initialize with the pre-trained VIT model, but we fine tune it on sketch data because the pre-trained version doesn't really work with sketches that well. Okay. For the image encoding, we just use a clip VIT model. So that's that. Now, the way the further architecture is decided as follows. So we essentially take the image and we want to come up with a representation of the image which is sensitive to the particular object that we have, right? Which attends to the particular object. So because the image actually can contain a large scene, we want to really localize the particular object. And therefore, what we do is to do some sort of attention. So we take the CLS token from the VIT sketch encoder, and we take each of those representations, from of individual patches of the overall or of the original image, and then do a dot product. So we basically just do a simple dot product as is shown here. So you take the CLS token of the sketch and the images patch representations from the clip image encoder, right? And you compute these alphas. They basically tell you how similar these patches of the image are to the sketch. Now, these are the weights that you use so as to basically get an attended image representation HI. Right, this is the attended image representation, which is then average pulled and really used as the overall image representation here. Okay, so that's that. Now the model is trained end to end using 5 different loss functions that you see here. Many of these loss functions are specifically tuned for the particular CSTBIR task. Okay. So these are the 5 loss functions. So contrastive loss. So essentially, of course, we want to ensure that the query and the image should be as close to each other as possible. So therefore, we basically take the CLS token representation from the text side, and then we basically take the HI average that we have gotten, sketch attended query representation in that senses, and then we compute the influency loss between them. Right, so we want to ensure that query and image pairs which are positive should be ranked higher compared to the query negative image pairs or image negative query pairs. Okay. Similarly, we also experiment with object classification. So we want to ensure that the text can help us detect the right object class given the 200 plus object classes that we have. Similarly, what we want to ensure is that given the sketch image, we want to ensure that we come up with the right class label. This is a multi-class classification problem. So that's the object classification loss, those 2 losses, right? Then we have the object detection loss. So on these images, fortunately, because of visual genome, we also have the object boundaries nicely recognized. And therefore, we can actually use the object detection loss on the original image so as to compute this object detection intersection over union, which can be used as an object detection loss. Lastly, we have a sketch reconstruction loss. So you want to ensure that, if you basically have a reasonably good image, which is attended by the sketch, then we must be able to reconstruct the sketch back. And that is why we have a sketch reconstruction loss, which comprises of 8 blocks of convolution, batch norm, and ReLU. And then finally, the sketch reconstruction loss is expressed in terms of binary cross entropy loss and the dice loss. Okay. So we use a linear combination of these losses so as to define the overall loss and then do the training. Now, how do the results look like? So, these are the image retrieval results on test 1K and test 5K datasets. So we compare our method with 3 different types of methods: sketch-based methods, text-based methods, and sketch+Text-based baselines, right? So we compare them on 2 different metrics: recall at K, and also on median recall, right? Median recall. So median recall is basically computed as median of the recall over the entire test set. So we have results over the 2 test sets, T1K, test 1K, and test 5K. So what do we observe? So for the sketch-based image retrieval, we have, of course, typical baselines like doodle to search and deep SBIR, but we also design yet another baseline called as VIT-based Siamese network, where we basically have 2 ImageNet pre-trained VIT encoders for sketch and image modalities, both of them going to the 2 towers, and it has been trained using InfoNC loss. So it's a really competitive baseline in that sense. So for the text-based baseline methods, we use the standard visual BERT, wilt, and clip kind of methods. For the composite sketch+Text methods, which can take both sketch and text together, we basically have the standard 2 baselines, TIRG and transformer, but we also design a 2-stage method. This 2-stage method essentially uses VIT trained for sketch classification. In the first stage, basically, we use a VIT which has been trained for sketch classification to obtain the object name. So remember, we have like 200 plus object names in the data set, right? And we basically use the first stage VIT-based sketch classifiers just to get the object name. And then we insert this object name into the incomplete text query, complete the full text query, and then use a pre-trained clip model so as to get the matching images, retrieve the relevant images. Okay. Now, object names could be sometimes nasty, they could be ambiguous and so on. So therefore, we also experiment with yet another baseline, 2-stage description-based baseline, where once we have figured out the object name, we insert the object description rather than the object name into the incomplete text query so as to get the full text query, pass it to the pre-trained clip model, and get the retrieve the relevant images. What do the results show? The results show that our method performs the best clearly, right? In fact, what we observe is that text-based methods perform better than the sketch-based methods, and sketch+Text-based methods perform better than the text-based methods. Okay. STNET actually performs the best, but STNET actually is better even than the 2-stage baseline. And this sort of happens because if you look at the 2-stage, just object name-based baseline, well, there are incomplete semantics in the object name. Several times, the object name doesn't really capture everything. A second problem is that object names could be ambiguous. For example, mouse, bat, star, they are all ambiguous names. It's actually even better compared to the 2-stage description-based baseline. And the idea is that descriptions sometimes can be very generic in nature. Although in this particular case, we actually obtained 7 descriptions per object name by using ChatGPT kind of models and also in a human way. But even then, the 2-stage description-based baseline cannot really make up for the loss in terms of the generic nature of the descriptions. Now, these are the kind of results that we obtain for a particular query, black star with a yellow outline. Okay. Now, ground truth object is, of course, star, and the 2-stage baseline was able to nicely get black star. And the 2-stage description is this black luminous celestial body with a yellow outline. Okay, black luminous celestial body is basically the representation for the black star. Okay, description for the black star. Now, what do you observe? You observe, and here are results, top 5 retrieved results shown for this query using different methods. VIT Siamese is the best sketch-based method, clip is the best text-only method, and 2-stage methods and STNET are our sketch+Text-based methods. What do we observe here? This is a ground truth image, okay? So this is really a black star with yellow outline, black star with yellow outlines, okay? So what do we observe? We observe that our method can really nicely retrieve that as the top 1 result. Okay, of course, the others that come up, some of them may be relevant, some of them are not, but the top 1 result is really good. VIT sketch only baseline just does not work, right? I mean, it basically sometimes gets this stop sign, sometimes some luminous object, but it's basically just a sketch-based baseline in that sense. Now, clip, basically, remember, it's just text-based baseline. So it just uses black, black with a yellow outline. Now, so basically it just retrieves black images, anything black, with seemingly yellow outline, but not really, right? 2-stage method, black star, it got confused. So these guys are, of course, stars, right? But not really the celestial body star. The 2-stage description baseline thinks of this as black star. Now, black luminous celestial body, right? So this is also celestial body, but, not really black, but that's what we retrieve from the 2-stage description based method. STNET model really gives the good results. We also tried to do some evaluation study on test 1K dataset so as to understand if it is really important to have both Sketch+Text and also is it really important to have all the loss functions that we had for our architecture. It sort of is seemingly very clear that Sketch+Text is super important compared to only Sketch or only text. But also what is important to see is that in these 3, 4, 5, 6 methods, we have removed 1, 1, 1 loss functions each, and then we observe that there is a drop in the matrix. And what we observe is that, so removing any of these 3 losses basically hurts. What we also observe is that removing the classification loss in this model number 4 basically hurts the most, right? Hurts the most in terms of matrix. Lastly, these are the results on our open category test set. So remember, open category test set is very complex, no representation of this object category in the train at all, and these are really difficult to name objects. So what we observe is that, yes, the matrix here are relatively much worse compared to the matrix on the test 1K and test 5K datasets. However, we observe that even in this complex setting, our STNET is most robust compared to the other baseline methods. Here are some more results. So essentially, if you're searching for this guy called capybara on a slide being fed red ice cream, and these are the top 5 retrieved results using our method, you basically get the top 1 result right. And that's also the ground truth result. By the way, those highlighted in green are the ground truth results. Now, for example, for this one, pair of, this animal is okapi feeding on green grass. You observe that, yes, our method comes up with reasonably right output, although this is the ground truth one, which basically our method detects as the second best result. So in conclusion, in this paper, we talked about a new problem definition, CSTBIR, Composite Sketch+Text-based image retrieval. We motivated why this kind of problem setting is required for difficult to name but easy to sketch objects and easy to express in text but difficult to sketch text descriptions. Right? So towards this problem, we contributed a new data set comprising of 2 million queries and 108K natural scene images. Remember, these queries comprise of incomplete text and crude sketch images. We also proposed STNET, Sketch+Text Network, as a method towards solving the CSTBIR problem, which comprises of pre-trained multimodal transformers to encode sketches, text, and images. It also uses hand-drawn sketch to localize relevant objects in the natural scene images by doing object detection as a loss. It encodes the text and image to perform image retrieval. Finally, it uses a combination of these 5 loss functions: contrastive loss, object classification loss, sketch-guided object detection loss, sketch reconstruction loss, object classification loss, both for the sketch and the text, so as to be able to obtain really good results. Now, our method has broad applications in many other domains, like searching for missing people, given sketches of how that missing guy looked like, and also searching for a product in digital catalogs, again, given a sketch of the product and given a large catalog of relevant products. Thanks so much. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.